So good afternoon everyone. So in this session we will be discussing types of organic reactions. Yes, yesterday itself we have started discussing about types of organic reactions. Okay, so today we will be looking back into it again. So again we will be discussing little more clearly. So what are the types of reactions we have, and so how the reactions are transforming from reactants to products. So during this transformation I told you there will be something called intermediate or transition state. So what are these reactive intermediates also we will be discussing today. Okay, so now let me go through the yesterday's one. Yeah, so here, so tell me what we have studied in the last class. So the reactants will convert into products. Okay, so during this transformation, so there is something called intermediate formation takes place, right, and it will be giving us product. So what are these reactive intermediates we need to know. Okay, so these reactive intermediates examples here I am mentioning something like carbocation. So what exactly I will tell you, carbocation, this is a one example, and the next carbene anion. Okay, so carbocation means on the carbon atom there will be positive charge. So carbene anion means on the carbon atom there will be negative charge. Okay, it means in the compounds of organic compounds on the carbon there will be positive charge, okay, or negative charge, or it can be also free radicals. So I will explain you what exactly free radicals also. Okay, so on the carbon atom there will be one electron, like one odd electron will be there. Okay, these are the important like intermediates we have. So along with this we also have carbenes. Okay, carbenes, okay, and nitrines. These are the intermediates, and also we have one more called benzene. So these are the intermediates we have. Okay, so now as this is a very basic bridge course, I will be focusing on discussing about carbocation, carbene anion, free radicals in the upcoming slides. Okay, so now those who joined online, I mean in the live session, so please click on the like button so that I can understand how many are really following the class. Yes. So now, so these are the things we have, intermediates, we will be discussing this also. Now once again we will be discussing about what are the types of organic reactions we have. Types of organic reactions. Okay, yeah. So what are the types I told you yesterday? Addition reactions and substitution reactions. The next, elimination reactions, next rearrangement, right, rearrangement reaction, and the last one is pericyclic reactions. Okay, so in your syllabus, so these are the important things: addition, substitution, elimination and rearrangement. These are the important things. In pericyclic only one or two reactions are there as per your syllabus, so you can just go through that, that is enough. Okay, so now let us understand what exactly addition reactions. So addition reactions in which to the substrate we will be adding some group, okay, group of atoms I can say. For example, here what we have written, so addition reactions you can observe here. So to this unsaturated compound, so tell me whether it is saturated or unsaturated. Unsaturated, at least one pi bond if it is present in the given hydrocarbon, so we can consider it as unsaturated, right. Now to this I am adding hydrogen in presence of metal catalyst like nickel we can use, palladium we can use, or platinum we can use. Okay. So what we are doing, so this is the substrate, to that we are adding this hydrogenation, like hydrogen we are adding now, so we can call this process as hydrogenation. Okay. So now what happens is, I am writing that compound as it is, CH2 we have. Okay, here whatever the white color bond which consider it as pi bond, now that is removed, to that each of this carbon this one hydrogen is added like this. See, to the substrate, if you observe, to the substrate we have added some new groups or new atoms, but we haven't removed anything, right? So that is what the addition reaction, something will be adding, some groups will be added to the substrate. This is what happens in the addition reactions. Okay. So now this simple addition I have discussed. Now some in few cases electrophile is involved in the addition reactions. So we can say electrophilic addition reaction. Sometimes nucleophile is involved in the addition reactions. That case we will call it as nucleophilic addition reaction. Okay. So now here let me take this CH2, again same thing I am taking CH2, to this I am adding HBr. We know HBr is an acid, right? So it will releases H plus ion and Br minus ions, right? So now here H plus is there now. So tell me, H plus means it is having electrons, or is it electron rich or electron deficient? I am asking about H plus. Electron deficient. So proton H plus is electron deficient because it is have no electrons. It is having 0 electrons now, right? So whatever the 1 electron is there, that is taken by bromine by this from the covalent bond, and it is becoming Br minus. So we can call H plus as electrophile. We can call proton as electrophile. Okay, because it is electron deficient only. So now during the chemical reactions, see, reactants combining to form products, but during this process sometimes some stages are involving, intermediate stage we are saying. Okay. So during that stages, during the each of that steps, so the slowest step during the process is considered to be rate determining step. It means how much fast, how much slow that reaction is taking place, complete kinetics is given from that rate determining step, that is what the slowest step of the reaction. Okay. So now while adding this HBr to this alkene, addition of this H plus ion is there now, that is what electrophile. Addition of this H plus ion to this alkene is rate determining step. What is that? Rate determining step is addition of H plus ion. Okay. So now since electrophile is involving in the slowest step, that is what rate determining step, we can call this mechanism as electrophilic addition reaction. Okay. If a nucleophile is involved in the rate determining step, addition reaction, nucleophilic addition reaction. Hope it is clear now. Now you can add this so that we will be getting, see, I am writing as it is. See, now it is H plus electron deficient, it requires electron. See here pi bonded electrons are loosely bonded electrons. So this is the reactive site now. So these electrons are given to this H plus ion. So that carbon, now this bond is forming between this carbon and hydrogen. So can I put a hydrogen here? Yes. Now this carbon lost these electrons now, these pi electrons, so that this carbon should get what charge? Positive charge. Yes, this is a positive charge carbon, right? To this, what is the negative part of this HBr? Yes, that Br minus should be added at the negatively charged species. See, chemistry, organic reactions are very easy. Just you need to identify which is electrophilic site, which is nucleophilic site, and make a bond between them. That's it. See, first of all, what you told, this is electrophilic site, so that this nucleophilic electrons are added to here, that is done. Again here electron deficient site, it means electrophilic site again, Br minus, can I say nucleophile? Yes. So this nucleophile go and attack here, that's it, over our reaction. So write the product CH2, CH2, here one H we added in the first case, one Br we added in the second case, right? Hope it is clear. So did we added the groups or do we removed anything? No, we just added H and Br to this. So we can call addition reaction only, right? Hope it is clear. Now this is an example for what? which addition? Electrophilic addition, right? Now I am taking one more compound here. This is what? Carbonyl compounds like aldehydes, ketones we will be calling now. Yes, this is an example of aldehyde. So to this, see here how can we identify what kind of reaction is taking place? See here, this carbon attached to the oxygen. Now which is electronegative, carbon or oxygen? So now these pi bonded electrons are taken towards which atom? The electronegative atom, that is oxygen side. Therefore, what is the charge we are creating on this carbon? Yes. So now partial positive charge is arising on this, and here it will be getting partial negative charge. See, partial positive is nothing but this is electron deficient site only now. Positive charge there means what we can understand? There is electron deficiency on that carbon, right? So can I say this is electrophilic site? Yes. So this is the electrophilic site. Now whatever the nucleophile we are taking, see Nu minus means, let us say this is a nucleophile. It means it is having electrons. Now since it is having electrons to donate and this is electron deficient to accept, therefore a bond is forming between them. That's it now. So when it is added, carbon valency should be satisfied. See, already 4 bonds are there, but this bond is getting polarized towards oxygen. Therefore new incoming group is entering here, and what we are expecting here, what is the product? RC. Tell me RC, this side H as it is I am writing. Okay, see this bond, pi bond is taken by oxygen, so that it will become O minus. Yes or no? And what is the new group entering onto the carbon? Nucleophile, Nu. Yes, this is the product. That's it. Simple, right? Any confusion? No. Now tell me, to this I will be asking you one question now. Now I will be giving you CH3 COH acetaldehyde. What is the name of this compound? Acetaldehyde. To this I wanted you to add HCN in basic medium like NaCN I have mentioned here. So what is the expected product here? NaCN you can add. Yes, tell me what is the product here? How can we understand this kind of reactions? Very easy, just follow the above method. Yes, oxygen is more electronegative, so it will drag these pi electrons towards itself and creates positive charge. Yes, what I can do next? Now how can we understand here? See, here I have given HCN, here I have given NaCN. So what does it saying here? We know sodium, always remember whenever alkali group is mentioned, that is electropositive now, alkali metals are electropositive, so it will definitely have positive sign. So this remaining sign will be negative. So what we have here? Cyanide ion, Cn minus. So what is our nucleophile in this reaction now? Nucleophile, electron rich species is what? Cn minus. So now this negative charge will attacks on that carbon, that's it. So what is our final product here? CH3 CH, this O minus it will become, and this will go and attack on the carbon. So that we will be having something like cyanide here. That's it. Okay. So here we have negative and here we have Na plus. Like this also you can understand. You know, whenever we are using this HCl, it's a weak acid. If we do not use this, reaction won't happen. Why it won't happen? Because I am saying this is a weak acid. So generation of Cn minuses does not takes place easily from HCN itself. Okay. So due to that reason, if we use this reaction in basic condition, so basic condition I have mentioned like this, NaCN. So in this we directly have Cn minus now, so that will be the nucleophile. Now after this, so since we are using basic condition, that OH minus and this H plus ion forms water now. So from that water one H plus ion is taken by this O minus, so that it will become CH3 CH this side, Cn here, and C O minus and H plus from water, so that it will become OH. And what is the remaining thing? OH minus from water and Na plus, that will be NaOH. You can understand like that. Okay. So this name of this compound is cyanohydrin. What is that? Cyanohydrin. Hope it is clear. No confusions now. Yes. So you can make a note of this. See what is involved in the rate determining step. This addition of nucleophile is a rate determining step. Yes. So just make a note so that we will discuss few other things also. Now I will be asking you one logical question, simple easy question. See, what is attacking reagent here? Nucleophile, Cn minus is the nucleophile is attacking here. So now tell me, in order to attack by this Cn minus, so which case is easy? Cn minus, it means this is electron rich. If more is the electron deficiency on the carbon, more easily the Cn minus can attack. Always remember, nucleophilic attack will be easy whenever there is more electron deficiency on the carbon, right? So now I will be giving you one question here. See, CO R H, like this I am writing. So let us make it CH2, CH3 I am writing. So here one more thing I am making, CO H CH2, and here I am writing some group like nitro group. Okay. So now where this nucleophile attack is easy, Nu minus nucleophile attack, whatever it is, Cn minus or anything you can consider. So nucleophile attack is easy in which case? Either in A case or in B case. How can we understand this kind of concepts? You will be studying about this in aldehydes, ketones, carboxylic acids, but I just wanted to give you now itself, the clarity you should maintain from now itself. Tell me, see here we have alkyl group only now, like methyl group we have. Here alkyl group is there, methylene group is there, along with that nitro group is there. Actually we know nitro group, NO2, nitrogen is more electronegative group now. It means this nitro group is like more electronegative group, you can say, in properly we can say electron withdrawing group. See, this is Anshika, not in one ma, it will be attacking of nucleophile takes easily in second case. I will explain you, listen here. See, this nitro group is called here it as electron withdrawing group. What is that group? Withdrawing group means it will withdraw the electrons towards itself. It means whatever the electron density present here, so that will be dragging towards this nitro group. Now what is the charge it is creating on the carbon? If it is withdrawing electrons towards itself, and this oxygen also withdraws electrons towards itself. Here also just this oxygen is withdrawing electrons towards itself. This scenario is same in both cases, but here we have just methyl group, here we have nitro group along with the methylene group. So due to the presence of this nitro group, it will withdraw the electrons towards itself and creates more positive charge, more electron deficiency on this. So now tell me, nucleophile is electron rich, and here this is electron deficient, this is also electron deficient, but which is more electron deficient? Here. Why? Because of this electron withdrawing group presence. So due to this reason, nucleophile attack is easy on more electron deficient carbon. So what we can understand from here? Electron withdrawing group containing aldehydes, ketones are more reactive towards nucleophilic addition reactions. Hope it is clear. Now I will be giving you one example. You can write it in your notes. CO, write the order for this, CH2, ERG means electron releasing group. Another example, So 1, 2, 3. So tell me, what is the reactivity order? Reactivity order for this. Reactivity order towards nucleophilic addition reaction. Which is more reactive? 3, 2, 1 or 1, 2, 3. So Anshika, you can also try for this question. Yes, tell me. Electron withdrawing group is present now. So what I told you, due to the presence of electron withdrawing group, it creates more positive charge here, more electron deficient. So therefore it is more reactive. So I can say 3. Here electron releasing group is there. It will release the electrons and decreases the electron deficiency. Decreases the electron deficiency. This is increases the electron deficiency. So presence of electrons are more here. Nucleophilic attack is little difficult when we compare with these two things. So that's why it is having least reactivity. Hope it is clear. So you can write electron withdrawing group containing carbonyl compounds are more reactive in nucleophilic addition reactions. Hope it is clear. Hope it is clear now. Yes. Yeah. So this is about nucleophilic addition reactions. Okay. So now we have studied electrophilic addition, nucleophilic addition reactions. Okay. Then next we also need to study about free radical addition reactions, FAR, but I am not going to discuss that now itself. We will be discuss that in the like hydrocarbon chapter. Okay. So now let us discuss about substitution reactions. Substitution reactions. So here we have two types. What I told you, nucleophilic substitution reactions and electrophilic substitution reactions. Okay. So now nucleophilic substitution means, see, substitution, the word itself saying now we are substituting a group with some other group, something like displacing the groups, right? So we can also call substitution reactions as displacement reactions also. Okay. So now look here. See here on this methyl group we have chloride ion. So we are calling it as methyl chloride. So now tell me, what is the electronegativity difference between this? Which is more electronegative? Chlorine is more electronegative, right? Since chlorine is more electronegative, these bonded electrons are there now. So that will be dragging towards which atom more? Chlorine side. So it will be taken towards chlorine, therefore it will be creating partial positive charge on the carbon. Yes or no? Yes. Now this is the electron deficient side, electrophilic side we can say, right? Again apply same concept. Electrophilic side we have identified in the substrate. Now this is our reagent. So this is aqueous NaOH. So sodium hydroxide in water, aqueous medium means. So here NOH minus Na plus. Now tell me, here electron deficient site is created and here we have electron rich hydroxide ion is there, right? So now this OH minus will go and attacks on this carbon because it is electron deficient now. Therefore this Cl minus is a good leaving group and Cl minus is going out, right? So what is the product we got now? CH3 OH and what removed out? Chlorine. So Cl minus Na plus, right? This is the product form. So now what you have understood here, see, Cl minus is displaced by OH minus, that's it. So we can say displacement reaction, there is no wrong in that. Or Cl minus is substituted by OH minus. So whatever the group going out from this substrate, we should call it as leaving group. What is that? Chloride ion is leaving group. What is the like incoming group is there now? That we can call it as incoming nucleophile. What is that? nucleophile. Clear now? Yes. So you can write this. You can write this. So what happening in the complete reaction? Substitution is taking place. What substitution? Nucleophile. Cl minus going out, which is a nucleophile, by OH minus coming in, that is also nucleophile. One nucleophile going out, another nucleophile entering, that's it. Hope it is clear? Yeah, you can write this. Yes. So after this, yeah. So now you need to understand one more thing here. If you look into these chemical reactions, whatever I have shown till now, you have seen bond cleavage you have seen. So what kind of bond cleavage? For example, let us say AA is a substrate. So what do we mean by substrate again? So something like reactants, this side product, that side I told now. Reactants again classified into substrate plus reagent I told you. Now let us say we have two types of substrates here, let us understand. AA type we have, something like AB type we have. Okay. So now here I am writing AB means these are two different atoms, you can understand. A is B and D different atom depending upon the polarity of this group, I mean polarity of this bond. Again polarity means it again depends upon electronegativity. Depending upon the electronegativity of these two atoms. For suppose electronegativity of B is more than A, electronegativity of B is more than A. So what happens to the bond? The bonded electrons, these two electrons taken by which atom? So taken by B. So therefore two electrons will be moving towards only one type of one side only. So that it is bond is breaking heterolytically, it means two unequal halves we are getting. What are the unequal halves here? A plus, B minus. So this is called heterolytic breakage or heterolytic cleavage. This is a basic thing, hope you know about this. Now here if you see to this AA type molecule, for this AA type molecule, so whenever we are supplying, say if I want to break this bond, see both A atom both are of same nature now. So therefore there is no polarity in this bond because their electronegativities are same. Okay. So in this condition, so what happens is due to the energies, all the things are same for both atoms, same now. So therefore bond cleavage will take place into two equal halves like this. One bond contains how many electrons? 2 electrons. So the 2 electrons, each one will take their own electron towards itself and forms A with dot. Okay. So this dot, if an atom contains one odd electron, we can call it as free radical. What is that? Free radical. So free radicals are formed by what type of cleavage? See, equal bond cleaving takes place. Now we can say homolytic cleavage. What is that? Homolytic breakage or homolytic cleavage. Hope it is clear. So when free radicals are generated, when bond is breaking homolytically. Okay. Now see here I am writing one example, chlorine, chlorine. Okay. We know on chlorine atom there will be 3 lone pair electrons like this. Okay. So now what happens, you know, so due to the electronic repulsions between these non-bonding electrons and these non-bonding electrons and here and here. So due to this electronic repulsion, this bond, the sigma bond get weaker, okay, due to the repulsions. Okay. So by supplying some little amount of frequency, the light energy which is required to break this bond. Okay. So now it will be cleaves into 2 equal halves. See, so I am indicating arrow with one head, single head. So it means single head represent one electron movement. Here see, complete both hands like this I am using. Both electrons are moving. But if I represent like this, only one electron is shifting. So that we are getting Cl radical, chlorine radical. Like this you can understand, right? Homolytic cleavage, heterolytic cleavage. Okay. This is also one thing you got to know. Okay. Now why I have discussed this thing here? We discussed about nucleophilic substitution reaction. No? Next we also need to discuss about electrophilic substitution as well as free radical substitution. So free radical substitution means, see here, simply I am taking methane, okay, to this I wanted to add chlorine, I want to react it with chlorine, so I can say chlorination of hydrocarbons, okay. So this process will take place in presence of something like sunlight or high temperature or some required frequencies, UV light is required, okay, like this we can mention, okay. So during this process, so whenever we are taking this in the excess quantity, so we will be getting CH3Cl as a product. This is our major product, other byproducts will also be there. So this is our major product depending upon the quantity we are taking this to, okay. So now how the reaction takes place here. So what I told you, first step is homolytic cleavage of this chlorine, Cl-Cl bond will be there now. So this will gives to chlorine radical. Again this chlorine radical, which is very reactive, this free radical is very reactive, okay, will react with this methane. So methane containing 4 hydrogens, now let us understand like this, tetrahedral geometry you can consider, but understand like this. So this radical will take one of the hydrogen from this chlorine, because see here always remember bond breakage should be takes place by considering that bond should be weaker when compared with the other bonds. So here all bonds are same, so that you need to break any of that bond. So like this electron pairing takes place with this hydrogen by this chlorine, so that what we are getting here, CH3, see out of this bonded electrons, one electron is remaining with chlorine carbon and one is going with hydrogen, so that we will get carbon with one electron and hydrogen is pairing up with chlorine, like chlorine one electron, hydrogen electron making a bond. So this is again a free radical, that is also reactive, again reaction keep on proceeding. So I am not going to explain complete mechanism here. So just now look what are the radicals here we have, one is methyl radical, another out of these 2 chlorines I have used only one more is there now. So this methyl radical plus this chlorine radical, so pair ups and forms methyl chloride like this. Hope it is clear. So what is the transformation we have seen? We have taken methane, it is forming methyl chloride. It means one of the hydrogen is substituted by chlorine radical. So can we say free radical substitution reaction in this case? Yes, this is about free radical substitution, okay. So you can write in the short form, you can write FSR and write this example, that's it. Okay. Now we need to discuss about electrophilic substitution reaction once if you complete this. Done? Yes, let us discuss electrophilic substitution reaction. See, here I am taking benzene ring. We know this is aromatic compound, so aromatic compound I am writing benzene, which is aromatic compound. So to this, we know on each carbon what we have, what is the formula of benzene? C6H6. It means on each carbon there will be one hydrogen, okay. So now to this I am adding Cl plus, I am reacting with Cl plus, consider like that, okay. And you know what happens in this process? So this Cl plus will replace this H plus, so that here we have got chlorine. So what kind of change we have seen here? See, this H plus is going out, this H plus is replaced by this Cl plus. It means H plus is also electrophile, right? Cl plus is also electrophile. So one electrophile is replaced by another electrophile. So can we say electrophilic substitution reaction? Yes, we can say electrophilic substitution reaction. Again, in which compounds it is happening? In aromatic compounds now. So we can say it as aromatic electrophilic substitution reaction. Hope it is clear? Yeah, you can write this example. Okay, so for more clarity you can write this proper example. So they will be giving in the books like this: benzene plus Cl2 and here FeCl3 they will mention, anhydrous from anhydrous, and they will write the product something like this, like this. So that is nothing but whatever we discussed above that happens in this case. Yeah. Done? Yes. The next we need to discuss about elimination reactions. So write the heading as elimination reactions. So elimination reactions. So here again substitution reactions we discussed now. There we have sub classification also, SN1, SN2, like that. We will be discussing about them later, but you got some clarity, like basic idea. So in elimination reactions also we have E1 elimination, E2 elimination and E1 CB elimination. Before that we have alpha 1 comma 1 elimination, okay, 1 comma 2 elimination, like this we have, okay, or we simply call it as alpha elimination. This is beta elimination. Okay, so this beta elimination is more important as per your syllabus, even alpha elimination also. Okay, so now in this beta elimination again it has three types. One is E1 elimination, E2 elimination, and other one is E1 CB elimination. E1 CB elimination you can write. Okay, E1 CB means unimolecular elimination reactions with conjugate base. Here it is, CB means conjugate base. Okay. So now let us understand what happens in the elimination reactions, especially this 1 comma 2 or beta elimination. It means, so let me write in this manner. Something like this we have. Okay. So here consider X is halogen like chlorine, bromine, iodine. Okay. Now what happens here is, we generally use here alcoholic KOH or NaOH under heating condition. Okay, this is a reagent we will be using. So which is a strong base, So now what happens is this base, strong base I am saying now. See, what is this 1 comma 2 means? We need to understand first. Halogen attached position is there, that carbon is first carbon, the adjacent carbon will be second carbon. So now the elimination will happen at 1 comma 2. It means atoms are eliminating from 1 comma 2 position. It means halogen from here and hydrogen from second carbon. Mean proton from second carbon. So how it happens means this base is there now. So this base will abstract a proton from here. Proton means this H plus will goes out, but the bonded electrons will stays with this carbon only na? Yes. So these bonded electrons are there na? So that will be shifting here. At the same time this halogen goes out from here as X minus. So what we are getting here finally? C double bond C. What are the remaining things here we have? H, here also H and one more H. So what are the groups we removed from here? One is H and X. You can just simply write HX just to understand what eliminated from there. Okay. So now what happening here, one hydrogen, one X halogen is eliminated from this position. So can we say elimination reaction? Yes. So this is what happens in the elimination reactions. Okay. So what we have seen, alkyl halide converted into alkene. This is alkene only now. This is alkyl halide. Okay. So now I will be giving you one example here. So just for make you more clear with this. Here I am writing Br. Here I am using alcoholic KOH heating condition. So tell me what happens? What is the product we can expect in this reaction? Yes. So first of all you need to identify what kind of reaction. Okay, alcoholic base under heating condition means elimination. Now elimination, where what we can expect here, so here halogen is there, it means this position is alpha position. So now the adjacent positions to this are called beta positions. Okay, now if hydrogens are present at beta position, that beta position hydrogen and this group should be eliminated. Now here we have two groups, means third group is hydrogen only now. Yes, here this is a carbon. On this carbon how many hydrogens are there now? 3. So now from where the proton elimination takes place? Where this base will abstract the proton? Yes. So always remember, internal alkenes are more stable. It means the double bond, alkenes are forming now. The double bond, if it is present inside of this alkyl chain, we can say internal alkene. If it is present at this terminal alkene. So what I am saying, which is more stable? Internal alkenes are more stable. So what is the reason for that? So we will be studying about the stability of alkenes in hyperconjugation topic. So there I will explain. Okay. Now from where we need to remove proton, what is the major product we can expect here? So this base will abstract a proton from here, and these sigma electrons are donated to the, so why it is donating like this means, you should also understand that. See, this is the sigma bond now. It means bonding molecular orbital. To this, in the exactly opposite direction, we will be having anti-bonding orbital. So whenever you are filling electrons into the anti-bonding orbital, these whatever the electrons are there in the bonding will get cancel out each other. So bonding minus anti-bonding will becomes 0. Okay. So how many bond means how many electrons here? 2. Okay. Here also we are donating like a pair of electrons from the bond, right? So it means these are falling into which orbital? Sigma star, anti-bonding orbital of this sigma bond. It means the bonds both cancel out and this bonds will get disappear from here. So that what is the final product we can get here? We have like this. So a pi bond is forming here. That's it. Hope it is clear. So this is a major product here. What is a minor product then? Minor product, see this is a beta, here also beta, no? So from there we can remove. Yes, tell me. Like this. See, I am not asking the byproduct or wastage, like you are saying H2O you are saying. So that is the, I mean by accepting H plus, that is a byproduct, or we can say the wastage. But we want what kind of products formed from this. So these are the two possible products. Okay, because beta protons are here and here. This can be abstracted, this can be abstracted. But which alkene is more stable? Internal alkene is more stable. That's why it is major and this will be minor. Okay. Next. Yeah. Elimination reactions. If you want, you can write. Done? Yes, let us move further. So next I told you rearrangement reactions. So what happens in the rearrangement? See, for example here, like this we have, okay, otherwise we will take this as alcohol, okay. So to this alcohol we are adding something like some acid reagent we are adding. So let us say HBr we are adding, okay. Now HBr is a strong acid, it releases what? It releases H plus, acid I am saying na H plus. Now what is the reactive site of the substrate? Where we can say where we can expect the reaction? See, always remember, simple carbon hydrogen never react in this, like in this kind of situations, okay. So now is there any pi bond to show reactivity? No pi bond. See, we have only this OH group is the reactive site here we have. So now this OH lone pair electron will take this H plus, and what it is forming? CH3, C, CH3, H, CH2, oxygen. Already one hydrogen is present here and one newly added hydrogen added. So now it is becoming positive charge on this oxygen. So now what you can understand from here, oxygen is getting positive charge now. So during the process what happens is this water will be removed out, because oxygen having positive charge it won't stay there, okay. So because oxygen is more electronegative than the carbon now, so which is more electronegative? Oxygen. So that's why it is leaving out. So if it is leaving out, how it will goes out? As water. Now what is the remaining piece we have? Tell me. C, CH3, H, positive charge. So this is called, what we can say on carbon, if we have positive charge, what we can say? I told you, reactive intermediates. Electrophile with carbon with positive charge. Carbocation. What is that? Carbocation. Now this carbocation attached to, directly attached to how many carbons? How many carbons are surrounding this carbon? See, it is attached only one carbon now to this carbon. How many carbons are attached? Directly attached carbons are only one. So we can say this is primary carbocation. What we can say? Primary carbocation. Now see here what I am doing. I am shifting this hydride from here to here like this, along with the sigma bonded electrons. So now what happens in that case? What happens in that case? So tell me, after shifting, what is the remaining piece we have? CH2. This hydride ion, I mean along with the sigma bond, we are shifting into this carbon. Now what happens? The bonded electrons are taken by hydrogen and shifted here. Na? So now what is the charge arising on the center carbon? Positive charge. Why it is positive? Because the bonded electrons are taken by this hydride ion only, right? So that we are getting a positive. Now tell me, this carbon is surrounded by how many carbons directly attached? 3. So we can call it as tertiary carbocation. So now out of these two carbocations, which is more stable? Tertiary carbocation is more stable than the primary carbocation. So again, what is the reason? How it is stabilized? We will be studying that in the applications of inductive effect, okay, and hyperconjugation. So this is very, very important. Lectures are will be provided later for this, okay. So there we will be understand. So which carbocation is more stable? So now what happened? Primary carbocation is rearranged to, so this process is called rearrangement, okay. So always a less stable intermediate converts into more stable intermediate, like less stable carbocation converted into more stable carbocation here. Clear now? Yes. So again, finally what happens after this rearrangement? Rearrangement, what happens? Whatever the negative part we have, Br minus, the nucleophile, it attacks on this position and gives us final product something like this. Like this. So this is our final product. Hope it is also clear. Yes. So types of reactions are done, all the types. Okay, so about pericyclic reactions we will be studying them in the classes itself, not required now, special discussion is not required here. Okay, so now yes, this is about the class. What I told you, there will be something called intermediates. What are the intermediates I told you? Reactive intermediates. So what I told you, reactants converts into products, but during this process we will be having intermediates or transition states I told you. So these are called reactive intermediates. These are short-lived species. Short-lived species. It means during this conversion they just live for some time and they will appear and they will disappear. Okay, so that is what the short-lived mean. Okay, so now, so what are the intermediates I told you? Carbocation, carbene anion, free radicals, carbenes, and the next nitrines. These things I told you. Now let us understand what exactly carbocation here. See now, here I have methyl chloride. Again I am taking methyl chloride. Okay, it means around the carbon how many bonds are there? 4 bonds are there like this. How many electrons are there in this now, tell me? Each bond contains 2 electrons, means 8 electrons. Now we know chlorine electronegative or carbon. So now these bonded electrons are taken by chlorine. Which kind of cleavage takes place generally in that? Homolytic or heterolytic? Heterolytic. Why? Because both atoms having different electronegativity. So we can expect to get CH3 plus and Cl minus. Now if you observe this carbon, how many atoms are there around it? 3 atoms like this. Okay. Now what is the charge here we have? Positive charge. Okay. Whenever we have 4 sigma bonds, so we can say sp3 hybridization. S, p1, p2, p3. So sp3 hybridization. Now here how many sigma bonds are there in the carbocation? So S, p1, p2. It means sp2 hybridization we can say. What is the hybridization here? sp2. Okay. Now is there any unpaired electron here? No unpaired electrons, all are paired up. So we can say carbocations are diamagnetic. Okay, clear up to here. Now again, what is the stability order I told you? Primary carbocation, tertiary carbocation. Which is more stable? Tertiary. So primary, secondary, tertiary we have. Tertiary more stable, then secondary, then primary. Explanation for this will be provided in the applications of inductive effect and hyperconjugation. Okay. So now this is the basic idea on the carbocation. Okay. So in more detail we will discuss in the reactive intermediates regular lecture. Okay. Next, carbene anion means on the carbon atom there should be negative charge. That's it. Okay. So for this, so whenever we have on carbon, if there is any acidic hydrogen, so what I am saying, any acidic hydrogen. So for example here 3 hydrogens are there now. I am highlighting one hydrogen from that. See, this hydrogen when we treat with aqueous base NaOH, so base will abstract this proton. Proton accepted and antonym. So what is the remaining species we have here? Tell me, what is the remaining part we have? R, C, double bond O, CH2, and what is the charge on carbon, positive or negative? Why positive or negative? Once again look, it is accepting H plus ion only. It means these bonded electrons are staying with carbon. It means that should be represented with negative. So this is a carbene anion, no? Yes, we can say this is carbene anion. Okay, so this is one of the example for carbene anions. So now carbon with 3 atoms, see this side 2 atoms, this is one more atom. So 3 bonds and with a negative charge. It will be like this. So what I can say, this is carbene anion. Now what is the hybridization for carbene anion? It is sp3. Okay, it is also all electrons are paired up, it is diamagnetic. Okay, so now what about free radicals? By bond cleavage we will be getting homolytic bond cleavage, we are getting free radicals. It means carbon with 3 bonded atoms and one orbital contain one unpaired electron. See, it is having one unpaired electron now. So can we call it as paramagnetic species? Yes. These are diamagnetic, free radicals are paramagnetic species. That's it. Okay. This is about the intermediates. Remaining intermediates we will discuss in the classes. Okay. Next, let us do some questions. Yes, answer this question. You can try to answer that easily. First one is, to this we are adding H pair, so that we are getting this one. So 1, okay, 1, yes, next. Look properly, what is the change you are observing there? Yes, we have removed Br from here and hydrogen from here, that's why it is becoming CH2. Just by proper observation you can get the answer. Okay, so I can say this is elimination. Now what about this? Look properly, what is happening? Yes, OH is here in the reactant, OH is here in the reactant. This is primary position, this is tertiary position. So OH is getting rearranged now, so we can say this is as rearrangement. Next tell me, is this substitution? Is this substitution or what? Look it properly. So we have added H plus here. Okay. No, it is not substitution. I can say it is not correct. See, what is the question? Incorrectly matched. So just look here. To this, if we are adding this HBr, so where do we need to add? See, we will write the reaction here. CH3, 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 CH, double bond CH2 we have. To this what we are adding? HBr. So in HBr, so what is the nature of HBr I told you? Acidic. So it will provide us H plus ions, right? So it will provide us H plus ion. So this H plus ion is taken by these pi electrons, right? It is taking this pi, and what it will become now? It will be CH3, C, CH3, CH, CH2. To this we are adding H. On this carbon it will be positive, right? This is what the carbocation we got. Now what type of carbocation it is? To this carbon, two sides carbon atoms are there, so secondary carbon. Now we know, tell me which carbocation is more stable, secondary, primary, tertiary, which is more stable? Tertiary. So it means secondary will be converts into tertiary by this methyl group shift, right? So that what we are getting? CH3, C, CH3, CH, CH3, here CH3, positive charge here. Here what we are adding finally? Br minus to this carbocation, and we are getting this product. That is what the transformation. So now we added H plus, we added Br minus to the substrate. So we can say it is addition reaction but not the substitution. Yes or no? Yeah. So this is the incorrect as per the representation. So we need to choose that option for, as the answer for this question, because they are asking incorrectly matched. Clear now? Yes. Next. Here I have one question for you. Yes, tell me. So tell me, what is the hybridization of carbons in this compound? A, B, C are the carbons. Identify their hybridizations. For A, sp3. Why sp3? How we are saying? 4 sigma bonds are there to around this. We can say sp3. Next, B carbon. sp2. Why sp2? 1 sigma, second sigma and third sigma, and 1 pi. Pi don't consider, only sigma. 3 sigmas means 1 is S and remaining 2 are P, so sp2. Next C carbon, sp2 only, again it is also having 3 sigmas and 1 pi. Now one last question based on previous classes. What is the difference you are seeing in that? So position, how position? See, position means parent chain, number of carbons in the parent should be same. How many are there in the parent chain in the first compound? 5. In this 4. Parent chain number of carbons are not same now, so we cannot go with position here. So position means parent chain carbon should be same, but position of substituents should be different. But that is not happening here. Chain isomers means they differ in the parent chain, but functional group is same here, chemical formula is also same. So we can say position, chain isomers here, right? They differ in the parent chain, right? And what about metamers? Metamers means to the same functional group, the alkyl groups are differ in the both sides. Here what is the alkyl group? Here we have ethyl. Here we have same functional group, but this side is methyl, this side is, this is 1, 2, 3 propyl it is. Okay, so same chemical formula both of them, but the functional group also same, but the alkyl group attached is different. So we can say them as metamers also. So chain isomers and metamers. So option 4 is correct. Hope it is clear. Okay, so if no doubts, we can wind up the class. If you have any doubts, you can ask me. No doubts? Clear in everything? Yes. So thank you for watching. So you can write your queries in the comment box so that we'll address them as per your requirements. So thank you for watching.